What if everything you thought you knew about the universe was just the tip of the iceberg? Picture this: a single teaspoon of material so dense it weighs as much as a mountain. Sounds impossible, right? Yet, this is just one of the mind-bending realities hidden in the cosmos. Today, we're diving into the universe's most extreme densities, phenomena so strange and powerful they defy everything we understand about space, time, and reality itself. From the crushing cores of neutron stars to the mysterious voids where matter seems to vanish, we're about to uncover 25 astonishing facts that will leave you questioning the very fabric of existence. So buckle up and prepare to explore the unimaginable. By the end of this journey, you'll see the universe in a way you never have before, ready to unravel the secrets of the cosmos. Let's begin. Now, let's zoom in on one of the universe's most extreme objects, neutron stars. These cosmic powerhouses are born from the explosive deaths of massive stars in events called supernova. When a star many times more massive than our Sun exhausts its fuel, it collapses under its own gravity, triggering a cataclysmic explosion. What's left behind is a neutron star, a city-sized object so dense that it defies imagination. To put it into perspective, imagine taking a single sugar cube's worth of neutron star material. That tiny piece would weigh as much as an entire mountain here on Earth. That's how mind-bogglingly dense these objects are. Neutron stars are essentially the crushed cores of dead stars, where matter is packed so tightly that protons and electrons merge to form neutrons. This extreme density creates an environment unlike anything else in the universe, where the laws of physics are pushed to their limits. And here's the kicker: neutron stars spin incredibly fast, some completing hundreds of rotations every second. This combination of density and speed makes them some of the most fascinating and extreme objects in the cosmos. But this is just the beginning. Next, we'll explore the mysterious and infinitely dense world of black holes. Now, let's venture into the enigmatic realm of black holes, where the universe's density reaches its ultimate extreme. Black holes are regions in space where gravity is so intense that nothing, not even light, can escape their pull. At the heart of every black hole lies a singularity, a point of infinite density where the laws of physics as we know them break down. Imagine squeezing an entire star or even a galaxy into a single, infinitely small point. That's the mind-bending reality of a black hole's core. But it's not just their density that makes black holes fascinating, they also warp the very fabric of space and time. Picture space-time as a stretched-out sheet. A black hole would be like a bowling ball dropped onto that sheet, creating a deep, inescapable well. Anything that gets too close, whether it's a star, a planet, or even light, gets pulled in, never to return. This is why black holes are often called cosmic vacuum cleaners, devouring everything in their path. Yet there's a boundary around a black hole called the event horizon, a point of no return. Once something crosses this invisible line, it's gone forever, lost to the black hole's insatiable hunger. But here's the twist: black holes aren't just destructive. They play a crucial role in shaping galaxies, influencing the movement of stars and even the formation of new ones. And while they remain shrouded in mystery, scientists continue to uncover their secrets, revealing just how vital these cosmic giants are to the universe's grand design. Next, we'll turn our attention to another dense cosmic wonder: white dwarfs, the remnants of stars like our Sun. Now, shifting our gaze from the all-consuming black holes, let's explore a different kind of cosmic density: white dwarfs. These stellar remnants are the final stage in the life cycle of stars like our Sun. When a star exhausts its nuclear fuel, it sheds its outer layers, leaving behind a hot, dense core. This core, now a white dwarf, is incredibly compact, packing a mass comparable to the Sun into a sphere roughly the size of Earth. To put it into perspective, a single teaspoon of white dwarf material would weigh as much as an elephant. But what keeps this dense object from collapsing further? The answer lies in a fascinating quantum phenomenon called electron degeneracy pressure. This pressure arises when electrons are squeezed so tightly that they resist being packed any closer, creating a force that counteracts gravity's relentless pull. Without this pressure, white dwarfs would collapse into even denser objects like neutron stars or black holes. Over billions of years, white dwarfs slowly cool and fade, eventually becoming dark, cold remnants known as black dwarfs. But here's the catch: the universe isn't old enough yet for any black dwarfs to exist. White dwarfs also play a crucial role in the cosmic recycling process. As they cool, they enrich the surrounding space with heavy elements forged during their star's lifetime, contributing to the formation of new stars, planets, and even life itself. So, while they may seem like the quiet end of a star's journey, white dwarfs are key players in the ongoing story of the universe. Next, we'll delve into the mysterious realm of quark stars, where matter takes on an even stranger form. Now, let's venture into the realm of the truly bizarre quark stars. Imagine a cosmic object so dense that even neutron stars pale in comparison. Quark stars are theoretical objects where matter is compressed to such extreme levels that it breaks down into its most fundamental building blocks, quarks. These particles, which usually combine to form protons and neutrons, are thought to exist in a free, unbound state within these stars. Scientists hypothesize that quark stars could form when the immense pressure inside a neutron star overcomes the forces holding neutrons together, causing them to disintegrate into a soup of quarks. This state of matter, often referred to as quark-gluon plasma, is one of the most extreme forms of density in the universe. But why are quark stars so elusive? For one, they're incredibly difficult to detect. Their properties are so similar to neutron stars that distinguishing between the two requires precise observations of their mass, size, and radiation. Additionally, quark stars are thought to be extremely rare, existing only under specific conditions that push matter beyond the limits of neutron stars. Some theories even suggest that quark stars could be the precursors to black holes, representing a transitional phase before matter collapses into a singularity. While no definitive quark star has been discovered yet, their existence could revolutionize our understanding of matter and the universe's most extreme environments. Next, we'll travel back in time to explore the density of the early universe, a period when the cosmos was unimaginably compact and hot. Now, let's take a step back in time, way back to the very beginning of everything. Picture the early universe not as the vast, sprawling expanse we see today, but as an unimaginably dense and compact point. This was a time when all the matter, energy, and space we know existed was squeezed into a volume smaller than a single atom. The density of the early universe was so extreme that it defies comprehension. Every particle, every force, and every bit of energy was packed together in a seething, chaotic state. This was the universe just moments before the Big Bang, a cosmic event that set everything into motion. But how did this incredible density lead to the universe we see today? The answer lies in the rapid expansion that followed the Big Bang. As the universe began to expand, the density of matter and energy started to decrease. Think of it like inflating a balloon. The more it expands, the more spread out its contents become. This expansion wasn't just a gentle stretching. It was an explosive, rapid growth that happened in a fraction of a second, known as cosmic inflation. During this period, the universe grew exponentially, cooling as it expanded and allowing particles to form and interact. Over billions of years, this process gave rise to galaxies, stars, and planets, all from that initial, unimaginably dense state. What's truly fascinating is that the remnants of this early density are still visible today. The cosmic microwave background, a faint glow of radiation that fills the universe, is like a snapshot of the universe when it was just 380,000 years old. This afterglow provides crucial clues about the density and temperature of the early universe. helping scientists piece together the story of how everything began. So, while the universe may seem vast and empty now, its origins tell a tale of extreme density and explosive growth, a story that continues to shape our understanding of the cosmos. Next, we'll explore how dark matter, though invisible, plays a crucial role in the universe's density and structure. Now, let's shift our focus to one of the universe's greatest mysteries, dark matter. While we can't see it, touch it, or even detect it directly, dark matter plays a vital role in shaping the cosmos. Imagine the universe as a giant cosmic web, with galaxies and clusters of galaxies strung together like beads on a string. What holds this intricate structure together? The answer lies in the gravitational pull of dark matter. Dark matter makes up about 27% of the universe's total mass and energy, far outweighing the ordinary matter we can see. But here's the twist: it doesn't interact with light or any other form of electromagnetic radiation. That's why it's invisible. So how do we know it's there? Scientists have observed its gravitational effects on visible matter, like stars and galaxies. For example, galaxies rotate faster than they should based on the visible matter alone. This discrepancy can only be explained by the presence of dark matter, whose gravity keeps these galaxies from flying apart. But dark matter's influence goes beyond just holding galaxies together. It also shapes the large-scale structure of the universe. During the early stages of cosmic evolution, dark matter acted as a scaffold, pulling ordinary matter into dense regions that eventually formed galaxies and galaxy clusters. Without dark matter, the universe as we know it simply wouldn't exist. Its gravitational pull is the glue that binds everything together, creating the cosmic web we see today. What makes dark matter even more fascinating is that it's not just a passive player. Its distribution affects how galaxies move and collide, and it even plays a role in the formation of the cosmic microwave background, that faint afterglow of the Big Bang we discussed earlier. By studying dark matter, scientists can uncover clues about the universe's origins and its ultimate fate. So, while dark matter remains invisible, its impact is undeniable. It's a key piece of the puzzle in understanding the universe's density and structure, reminding us that there's so much more to the cosmos than meets the eye. Next, we'll venture into the emptiest regions of the universe, cosmic voids, and see how they challenge our understanding of density in space. Now, let's step into the vast emptiness of cosmic voids, the universe's most desolate regions. While we've been exploring extreme densities, cosmic voids are the exact opposite: enormous stretches of space where matter is almost entirely absent. Picture a sponge. The dense clusters of galaxies are like the solid parts, while the voids are the empty holes in between. These voids can span hundreds of millions of light years, making them some of the largest structures in the cosmos. But don't let their emptiness fool you. Cosmic voids are just as fascinating as the densest objects in the universe. They challenge our understanding of how matter is distributed across space. According to the Big Bang theory, matter should be spread relatively evenly throughout the universe. Yet, cosmic voids reveal a patchy, uneven distribution, with vast regions nearly devoid of galaxies, gas, or even dark matter. This raises a critical question. Why does the universe have such extreme contrasts between dense clusters and these empty voids? One theory suggests that cosmic voids formed as a natural consequence of the universe's expansion. In the early universe, tiny fluctuations in density grew over time, with gravity pulling matter into denser regions. As these dense areas grew, the space between them became emptier, creating the voids we see today. It's like watching water drain from a sink. The water flows toward the drain, leaving empty spaces behind. In the same way, matter flows toward dense regions, leaving voids in its wake. Interestingly, cosmic voids aren't completely empty. They contain a sparse scattering of galaxies and faint traces of gas, but their density is so low that they're often described as the universe's deserts. Even dark matter, which permeates most of the cosmos, is scarce in these regions. This scarcity makes voids a unique laboratory for studying the effects of gravity and the behavior of the universe on the largest scales. What's truly mind-bending is how cosmic voids affect the universe's expansion. Because there's so little matter in these regions, the gravitational pull is weaker, allowing space to expand faster within voids than in denser areas. This uneven expansion can influence the motion of galaxies and even the path of light, bending it in ways that challenge our understanding of cosmic structure. Cosmic voids remind us that the universe is full of surprises. They show us that density isn't just about how much matter is packed into a space. It's also about the vast emptiness that defines the gaps between. As we continue our journey through the universe's most extreme densities, let's turn our attention to the heart of our own solar system, the Sun's core, where unimaginable pressure and density fuel the star that gives us life. Now let's journey to the very heart of our solar system, the core of the Sun. This is where the magic happens, where unimaginable pressure and density create the conditions for nuclear fusion, the process that powers our star and ultimately sustains life on Earth. Picture the Sun's core as a cosmic furnace, where temperatures soar to around 15 million degrees Celsius, and the pressure is more than 250 billion times greater than what we experience on Earth's surface. It's here, in this extreme environment, that hydrogen atoms are forced together to form helium, releasing vast amounts of energy in the process. This energy, generated through nuclear fusion, is what makes the Sun shine. Every second, the Sun converts approximately 600 million tons of hydrogen into helium, releasing energy equivalent to billions of nuclear bombs. This energy radiates outward from the core, traveling through the Sun's layers until it reaches the surface and escapes into space as sunlight. Without this constant fusion reaction, the Sun would simply fade, and life as we know it would cease to exist. But what makes the Sun's core so uniquely dense? The answer lies in the sheer gravitational force at play. The Sun's immense mass creates a gravitational pull so strong that it compresses the core to a density about 150 times that of water. To put that into perspective, a teaspoon of material from the Sun's core would weigh as much as a small car. This incredible density is what allows the core to sustain the high temperatures and pressures needed for fusion to occur. The energy produced in the core doesn't just keep the Sun burning, it also drives the solar wind, influences the orbits of planets, and provides the warmth and light necessary for life on Earth. Every ray of sunlight that reaches us began its journey in the Sun's core, traveling for thousands of years through the star's dense layers before finally breaking free into space. It's a reminder of how interconnected our solar system is, and how the Sun's core, despite being millions of kilometers away, plays a direct role in our daily lives. As we marvel at the Sun's core, we're reminded of the delicate balance that makes life possible. The extreme density and pressure at the heart of our star are not just scientific curiosities, they're the very foundation of our existence. And as we continue our exploration of the universe's most extreme densities, let's turn our gaze outward to the discovery of ultra-dense exoplanets that challenge everything we thought we knew about planetary formation. Now, let's venture beyond our solar system to explore the fascinating world of exoplanets, planets that orbit stars other than our Sun. Among these distant worlds, some stand out for their extraordinary densities, defying our expectations of what planets can be. Imagine a planet so dense that it's made almost entirely of diamond, or another so packed with iron that it's heavier than anything we've ever seen in our own cosmic neighborhood. These ultra-dense exoplanets are not just scientific curiosities, they're rewriting the rules of planetary formation. One of the most intriguing examples is the so-called Diamond Planet, officially known as 55 Cancri. This exoplanet, located about 40 light-years from Earth, is believed to be composed largely of carbon, with a significant portion of it crystallized into diamond. Scientists estimate that this planet's core could contain as much as 1/3 of its mass in diamond form. To put that into perspective, if you could mine this planet, its diamond content would be worth quadrillions of dollars, though, of course, getting there is another story entirely. But beyond its glittering allure, this planet challenges our understanding of how planets form. How does a world become so carbon-rich? The answer likely lies in its star system's unique chemistry, where carbon was far more abundant than oxygen during its formation. Then there are the iron-rich exoplanets like Kepler-10b, a scorching hot world with a density so high that it's thought to be made mostly of iron. This planet, which orbits incredibly close to its star, has a surface temperature hot enough to melt metal, yet its core remains solid due to the immense pressure. Its density is so extreme that it's nearly twice as dense as Earth, despite being only about 1.5 times its size. Planets like Kepler-10b raise questions about how such high concentrations of iron can accumulate in a single world. Did they form from the remnants of a star's core, or were they shaped by violent collisions that stripped away lighter materials, leaving behind a dense metallic core? These ultra-dense exoplanets are more than just cosmic oddities. They're windows into the incredible diversity of planetary systems. They challenge our assumptions about how planets form and evolve, showing us that the universe is far more creative than we ever imagined. From diamond worlds to iron giants, these discoveries remind us that there's still so much to learn about the cosmos. And as we continue to explore, who knows what other extreme densities we might uncover. Next, we'll turn our attention to the dense heart of our own galaxy, the center of the Milky Way, where a supermassive black hole and a dense cluster of stars shape the very fabric of our cosmic home. Now let's journey to the very heart of our galaxy, the center of the Milky Way. This region is a cosmic powerhouse, home to a supermassive black hole known as Sagittarius A*, or SGR A* for short. This colossal black hole, with a mass equivalent to about 4 million suns, sits at the center of a dense cluster of stars, creating one of the most extreme environments in the universe. The density here is staggering, with stars packed so tightly that they orbit at incredible speeds, some completing a full revolution around the black hole in just a few years. To put that into perspective, our Sun takes about 230 million years to complete one orbit around the galactic center. The gravitational pull of Sagittarius A* is so immense that it shapes the entire structure of the Milky Way. It acts like a cosmic anchor, holding the galaxy together and influencing the motion of stars, gas, and dust across vast distances. But it's not just the black hole that makes this region so dense. Surrounding it is a bustling stellar metropolis where stars are born, live, and die in a chaotic dance. Some of these stars are so close to the black hole that they experience extreme tidal forces, stretching and compressing as they orbit. Others are flung outward at incredible speeds, creating a dynamic and ever-changing environment. This dense core also plays a crucial role in the evolution of our galaxy. The intense gravitational forces and radiation from the black hole and surrounding stars can trigger star formation in nearby gas clouds, while also stripping away material from other stars, leaving behind dense remnants like neutron stars and white dwarfs. It's a place of extremes where the laws of physics are pushed to their limits, and yet it's also a place of creation where new stars and planetary systems are born. The center of the Milky Way is a reminder of the incredible forces at work in our universe. It's a region where density and gravity reign supreme, shaping not just the stars and black holes within it, but the entire galaxy we call home. As we continue to study this mysterious region, we uncover more about the forces that govern the cosmos and our place within it. Next, we'll explore another extreme density phenomenon, gamma-ray bursts, the most energetic events in the universe, and how they're linked to the collapse of massive stars or the collision of neutron stars. Now, let's turn our attention to one of the most explosive and mysterious events in the cosmos: gamma-ray bursts. These bursts are the most energetic phenomena in the universe, releasing more energy in just a few seconds than our Sun will emit over its entire 10 billion-year lifetime. But what makes them so powerful? The answer lies in the extreme densities involved in their creation. Gamma-ray bursts are often linked to the collapse of massive stars or the collision of neutron stars, events where matter is compressed to unimaginable levels. When a massive star reaches the end of its life, it doesn't go quietly. Instead, it collapses under its own gravity, forming a black hole or a neutron star. During this collapse, the star's core is squeezed to such an extreme density that it triggers a cataclysmic explosion, known as a supernova. In some cases, this explosion is accompanied by jets of energy shooting out at nearly the speed of light. These jets, packed with gamma rays, are what we observe as gamma-ray bursts. The density at the core of the collapsing star is so intense that it creates conditions unlike anything else in the universe, producing these incredibly bright flashes of light. But gamma-ray bursts aren't just born from collapsing stars. They can also occur when two neutron stars collide. Neutron stars are already among the densest objects in the universe, with a teaspoon of their material weighing as much as a mountain. When two of these ultra-dense objects spiral toward each other and merge, the resulting collision releases an enormous amount of energy in the form of gamma rays. This merger not only produces a gamma-ray burst but also creates ripples in space-time, known as gravitational waves, and forges heavy elements like gold and platinum. What makes gamma-ray bursts so fascinating is their sheer power and the extreme conditions they reveal. They offer us a glimpse into the most violent and dense environments in the universe, where matter is pushed to its absolute limits. By studying these bursts, scientists can learn more about the life cycles of stars, the behavior of matter under extreme pressure, and even the origins of the elements that make up our world. As we continue to explore the universe's most extreme densities, gamma-ray bursts remind us of the incredible forces at play in the cosmos. They are a testament to the universe's capacity for both destruction and creation, shaping the very fabric of space and time. Next, we'll dive into another intriguing concept: cosmic strings, theoretical one-dimensional objects with extreme density that may hold clues to the early universe. Now, let's shift our focus to a concept that sounds like it's straight out of science fiction: cosmic strings. These are theoretical one-dimensional objects, incredibly thin but unimaginably dense, thought to have formed in the early universe. Imagine a thread so dense that just a single inch of it could weigh as much as an entire mountain. Cosmic strings are believed to be remnants of the universe's infancy, formed during a phase transition when the cosmos was still cooling down after the Big Bang. These strings are not made of ordinary matter, but are instead defects in the fabric of space-time itself. They are so dense that they warp the space around them, creating gravitational effects that could, in theory, bend light or even distort the paths of galaxies. Scientists speculate that cosmic strings might have played a crucial role in shaping the large-scale structure of the universe, acting as cosmic seeds around which galaxies and galaxy clusters formed. However, detecting cosmic strings is no easy task. Because they are so thin and their gravitational effects are subtle, they remain elusive to direct observation. Some researchers suggest that we might find evidence of their existence through their impact on the cosmic microwave background, the faint afterglow of the Big Bang. Others propose that if two cosmic strings were to cross or snap, they could produce ripples in space-time known as gravitational waves, which we might detect with advanced instruments. Despite their theoretical nature, cosmic strings offer a fascinating window into the early universe. They challenge our understanding of density and space-time, pushing the boundaries of what we know about the cosmos. While we haven't found definitive proof of their existence yet, the search for cosmic strings continues to inspire scientists to explore the universe's most extreme and mysterious phenomena. Next, we'll explore another relic of the early universe, the cosmic microwave background, and how its uniform density provides clues about the universe's beginnings. Now, let's turn our attention to one of the most profound echoes of the universe's birth, the cosmic microwave background. This faint afterglow, often referred to as the oldest light in the cosmos, is a snapshot of the universe when it was just 380,000 years old. At that time, the universe had cooled enough for atoms to form, allowing light to travel freely for the first time. What we see today as the cosmic microwave background is the remnant of that ancient light, stretched and cooled over billions of years into microwave wavelengths. What makes the cosmic microwave background so remarkable is its near-perfect uniformity. The density of this radiation is incredibly even across the entire sky, with only tiny fluctuations, less than 1 part in 100,000. These minute variations, however, are crucial. They represent the seeds of all the structure we see in the universe today. Slightly denser regions in the early universe grew over time, pulled together by gravity, eventually forming galaxies, stars, and planets. Without these tiny irregularities, the cosmos would be a featureless void. But how did this uniform density come to be? Scientists believe it's a result of the rapid expansion of the universe during its earliest moments, a period known as inflation. This explosive growth smoothed out the universe, creating the nearly uniform density we observe in the cosmic microwave background. Yet, the slight variations we see are like cosmic fingerprints, offering clues about the conditions and processes that shaped the universe in its infancy. Studying the cosmic microwave background has revolutionized our understanding of the cosmos. It has provided evidence for the Big Bang theory, helped us measure the universe's age and composition, and even hinted at the existence of dark energy. The density of this ancient light is not just a relic of the past, it's a roadmap to the universe's origins and evolution. As we continue to map and analyze the cosmic microwave background with ever greater precision, we uncover more about the universe's earliest moments. Next, we'll dive into another extreme density event, the collision of neutron stars, and how these cosmic crashes create some of the heaviest elements in the universe. Now, let's shift our focus to one of the most dramatic events in the cosmos, the collision of neutron stars. When two of these incredibly dense objects spiral toward each other and finally collide, the result is nothing short of spectacular. To put it into perspective, neutron stars are so dense that a single teaspoon of their material would weigh about 1 billion tons. Now, imagine two of these cosmic powerhouses smashing together. The density involved in such a collision is almost beyond comprehension. When neutron stars collide, they unleash an extraordinary amount of energy, creating ripples in the fabric of space-time known as gravitational waves. These waves, first detected in 2017, provide scientists with a new way to observe the universe. But the collision doesn't just send out gravitational waves, it also produces some of the heaviest elements in the universe. Elements like gold, platinum, and uranium are forged in the intense heat and pressure of these cosmic crashes. In fact, a single neutron star collision can produce enough gold to outweigh the entire Earth. The process begins as the neutron stars merge, forming a dense, hot object that briefly exists before collapsing into a black hole. During this brief window, matter is squeezed and heated to extreme conditions, allowing atomic nuclei to fuse into heavier elements. These elements are then ejected into space, scattering across the cosmos and eventually becoming part of new stars, planets, and even life itself. It's a reminder that the very atoms in our jewelry, electronics, and even our bodies were once forged in the heart of a neutron star collision. What makes these events even more fascinating is their rarity. Neutron star collisions are incredibly rare, occurring only about once every 100,000 years in a galaxy like our Milky Way. Yet, when they do happen, they leave behind a legacy that shapes the universe in profound ways. By studying these collisions, scientists gain insights into the behavior of matter under extreme conditions, the origins of heavy elements, and the nature of gravity itself. As we continue to explore the universe's most extreme densities, we'll next turn our attention to hypergiant stars, massive yet surprisingly low-density objects that defy our expectations. Stay tuned to uncover how these cosmic giants challenge our understanding of density in the cosmos. Now, let's take a step into the realm of hypergiant stars, where the rules of density seem to flip entirely. Unlike the mind-bending compactness of neutron stars or black holes, hypergiant stars are cosmic giants that defy our usual expectations of density. These stars are among the largest and most massive in the universe, yet their density is surprisingly low. How can something so massive be so spread out? Let's break it down. Hypergiant stars like the famous Eta Carinae can be hundreds of times more massive than our Sun and millions of times brighter. But here's the twist: despite their enormous size, their material is spread so thinly that their average density is incredibly low. To put it into perspective, if you could scoop up a chunk of a hypergiant star, it would feel almost like a wispy cloud compared to the crushing density of a neutron star. This is because these stars are so vast that their outer layers extend far into space, creating a diffuse structure that's more like a cosmic balloon than a tightly packed sphere. What makes hypergiant stars so fascinating is how they challenge our understanding of density. While we often associate density with compactness, these stars remind us that density is simply a measure of mass spread over volume. In the case of hypergiants, their immense size means their volume is enormous, diluting their density despite their staggering mass. This unique balance makes them some of the most intriguing objects in the cosmos, as they push the boundaries of what we consider normal for stellar density. But there's more to the story. Hypergiant stars are also incredibly unstable. Their massive size and low density make them prone to dramatic outbursts, shedding huge amounts of material into space. These eruptions can create stunning nebulae and even influence the formation of new stars and planets. In a way, hypergiants are like cosmic sculptors, shaping their surroundings with their immense energy and material. As we marvel at these colossal yet low-density stars, we're reminded that the universe is full of surprises. Hypergiants show us that density isn't always about being compact, it's about the delicate balance between mass and space. And with that, we'll move on to explore another fascinating region of the cosmos, the Oort cloud, a sparse but massive collection of icy objects at the edge of our solar system. Stay tuned to uncover how this distant region plays a crucial role in the story of our cosmic neighborhood. Now, let's journey to the very edge of our solar system, where the Oort cloud stretches far beyond the familiar planets and into the cold, dark reaches of space. This vast, mysterious region is home to trillions of icy objects, each a frozen relic from the early days of our solar system. Despite its immense size, spanning up to 100,000 times the distance between the Earth and the Sun, the Oort cloud is incredibly sparse. If you were to stand in the middle of it, you'd likely see nothing but empty space, with the nearest object potentially millions of miles away. Yet, this seemingly empty region holds a treasure trove of cosmic secrets. The Oort cloud is thought to be the birthplace of long-period comets, those spectacular visitors that occasionally streak across our night sky. These comets are essentially chunks of ice and rock, remnants of the material that formed the planets billions of years ago. When a passing star or the gravitational tug of the Milky Way disturbs the Oort cloud, some of these icy bodies are nudged out of their orbits and sent hurtling toward the inner solar system. As they approach the Sun, the heat causes their icy surfaces to vaporize, creating the glowing tails that make comets so mesmerizing to watch. What's fascinating about the Oort cloud is how it challenges our understanding of density. While it contains an enormous amount of material, its sheer size means that this material is spread incredibly thin. To put it in perspective, if you gathered all the objects in the Oort cloud and compressed them into a single sphere, it would still be far less dense than even the most diffuse gas clouds in space. This sparse distribution makes the Oort cloud one of the least dense regions in the solar system, yet its influence is anything but small. The Oort cloud also serves as a cosmic time capsule, preserving the building blocks of our solar system in their most pristine form. By studying comets that originate from this distant region, scientists can gain insights into the conditions that existed when the Sun and planets first formed. These icy wanderers carry clues about the early chemistry of the solar system, including the presence of water and organic molecules, ingredients that may have played a role in the emergence of life on Earth. As we reflect on the Oort cloud, we're reminded that density isn't just about how tightly packed something is, it's also about the scale of the space it occupies. This distant, icy realm may seem empty, but its role in shaping the solar system and delivering comets to our skies makes it a vital part of our cosmic story. Next, we'll turn our attention to the interstellar dust that fills the space between stars and discover how this seemingly sparse material plays a crucial role in the birth of new worlds. Stay with us as we continue to unravel the mysteries of the universe's most extreme densities. Now, let's shift our gaze from the icy outskirts of the Oort cloud to the vast, seemingly empty spaces between the stars, where interstellar dust quietly shapes the cosmos. At first glance, this dust might appear insignificant tiny particles scattered across the void, barely noticeable against the backdrop of the universe. But don't let its sparse appearance fool you. Interstellar dust is a cosmic powerhouse, playing a vital role in the birth of stars and the creation of complex molecules that could one day form the building blocks of life. Interstellar dust is made up of tiny grains, often no larger than a fraction of a millimeter. These grains are composed of elements like carbon, silicon, and oxygen, along with compounds such as water ice and organic molecules. Despite their small size, these particles are incredibly important. They act as the seeds for star formation, providing the raw material that clumps together under gravity to form dense clouds. Over time, these clouds collapse, giving birth to new stars and planetary systems. Without interstellar dust, the universe would be a much emptier place, devoid of the dazzling stellar nurseries we see today. But the role of interstellar dust doesn't end there. These tiny particles also serve as cosmic laboratories where complex chemical reactions take place. On the surfaces of dust grains, atoms and molecules come together to form more complex compounds, including some of the organic molecules essential for life. Scientists believe that these processes may have played a key role in the origins of life on Earth, as comets and asteroids carrying interstellar dust delivered these molecules to our planet billions of years ago. What's truly fascinating is how interstellar dust, despite its low density, manages to have such a profound impact. The particles are spread so thinly that in most regions of space, you'd find only a few grains in a volume the size of a football stadium. Yet, over vast distances and timescales, their collective influence is immense. They absorb and scatter starlight, creating the beautiful nebulae we see in telescopes, and they help regulate the temperature of interstellar clouds, influencing how stars form and evolve. As we explore the density of interstellar dust, we're reminded that even the most seemingly insignificant parts of the universe can have a profound impact. This sparse, scattered material is a testament to the intricate balance of cosmic forces, shaping the stars, planets, and perhaps even the origins of life itself. Next, we'll delve into the cosmic web, a vast network of dark matter and gas that weaves the universe together on the largest scales. Stay with us as we continue to uncover the mysteries of the universe's most extreme densities. Now, let's zoom out from the scattered grains of interstellar dust and take in the grand tapestry of the universe itself, the cosmic web. Imagine the universe not as a random collection of stars and galaxies, but as an intricate network, a vast spiderweb stretching across unimaginable distances. This is the cosmic web, a structure made up of dark matter and gas woven together by gravity over billions of years. It's the backbone of the universe, shaping everything we see on the largest scales. The cosmic web is made of long, thread-like filaments of dark matter, invisible to our eyes but detectable through its gravitational effects. These filaments connect galaxies and galaxy clusters, forming a sprawling network that spans the entire observable universe. Along these filaments, gas flows, feeding the growth of galaxies and igniting the birth of stars. It's like a cosmic highway system, with galaxies as the bustling cities and the filaments as the roads that link them together. What's truly remarkable about the cosmic web is how it reveals the universe's underlying structure. If you could step back and view the universe from afar, you'd see a pattern, a web-like arrangement where galaxies cluster at the intersections of filaments, while vast, empty voids stretch between them. These voids, regions of extremely low density, are like the empty spaces in the web, while the filaments are the dense threads that hold everything together. Together, they create a delicate balance, a cosmic dance of density and emptiness. The cosmic web isn't just a static structure, it's dynamic, constantly evolving as gravity pulls matter along the filaments and into the nodes where galaxies form. This process shapes the universe on the largest scales, influencing how galaxies grow, merge, and interact. Without the cosmic web, the universe would lack the structure we see today, and galaxies would be scattered randomly, isolated from one another. Scientists study the cosmic web to understand the universe's history and its future. By mapping the distribution of galaxies and measuring the flow of gas along the filaments, they can trace the growth of the web over time. This helps us understand how dark matter and dark energy shape the cosmos, and how the universe has expanded and evolved since the Big Bang. As we explore the density of the cosmic web, we're reminded of the universe's incredible complexity. From the tiniest grains of interstellar dust to the vast filaments of dark matter, every part of the cosmos plays a role in shaping the story of the universe. Next, we'll turn our attention to another mysterious and dense phenomenon, primordial black holes, which may hold clues to the universe's earliest moments. Stay with us as we continue to unravel the mysteries of the universe's most extreme densities. Now, let's shift our focus to one of the most intriguing mysteries of the cosmos, primordial black holes. These hypothetical objects are thought to have formed not from the collapse of massive stars, like the black holes we're familiar with, but in the chaotic moments just after the Big Bang. Imagine the early universe, a seething cauldron of energy and matter, where tiny fluctuations in density could have created regions so dense that they collapsed directly into black holes. These primordial black holes could be as small as an atom or as massive as a star, and they might still be lurking in the universe today, hidden from our view. What makes primordial black holes so fascinating is their potential connection to dark matter. Scientists have long puzzled over what dark matter is made of, and while many theories point to exotic particles, primordial black holes offer an alternative explanation. If these ancient black holes exist in large numbers, they could account for the invisible mass that shapes galaxies and holds the cosmic web together. Unlike ordinary black holes, which are born from dying stars, primordial black holes would have formed before stars even existed, making them relics of the universe's infancy. The idea of primordial black holes isn't just speculative, it's grounded in the physics of the early universe. During the rapid expansion after the Big Bang, regions of slightly higher density could have collapsed under their own gravity, creating black holes without the need for stars. These black holes would have been scattered throughout the universe, some evaporating over time due to a process called Hawking radiation, while others might have grown by consuming matter or merging with one another. Detecting primordial black holes is no easy task. They don't emit light, and if they're small enough, they could be nearly invisible. However, scientists have proposed clever ways to search for them. For example, if a primordial black hole passes in front of a distant star, its gravity could bend the star's light, creating a temporary brightening known as microlensing. Observations of these events could provide clues about the existence and distribution of these elusive objects. The implications of primordial black holes are profound. If they exist, they could help us understand not only dark matter but also the conditions of the early universe. They might even explain some of the gravitational wave signals detected by observatories like LIGO, which could be the result of primordial black holes colliding. As we continue to explore the universe's most extreme densities, primordial black holes remind us that some of the cosmos' greatest secrets may still be hidden in the shadows, waiting to be uncovered. Next, we'll dive into the incredible density of magnetars, neutron stars with magnetic fields so powerful they defy imagination. Stay with us as we uncover more about these cosmic powerhouses and their role in the universe's most extreme environments. Now, let's turn our attention to one of the most extreme objects in the universe, magnetars. These are a special type of neutron star, but with a twist that makes them truly extraordinary. Imagine a neutron star, already one of the densest objects in existence, packing the mass of a star into a sphere just a few miles across. Now, take that density and combine it with a magnetic field so powerful it could strip the information off a credit card from hundreds of thousands of miles away. That's a magnetar. Magnetars are born from the explosive deaths of massive stars, just like regular neutron stars. But what sets them apart is their magnetic fields, which are 1,000 times stronger than those of typical neutron stars. To put this into perspective, the magnetic field of a magnetar is so intense that if one were located halfway between the Earth and the Moon, it could erase the data on every credit card on our planet. This incredible magnetic power comes from the extreme density of these objects, which twists and amplifies their magnetic fields to unimaginable levels. The density of a magnetar is mind-boggling. A single teaspoon of its material would weigh billions of tons on Earth. This extreme density is what allows magnetars to generate such powerful magnetic fields. The core of a magnetar is so densely packed that protons and electrons are forced together, creating a superfluid of neutrons. This superfluid spins rapidly, generating electric currents that, in turn, produce those colossal magnetic fields. It's a perfect storm of density and motion, creating one of the most extreme environments in the cosmos. But magnetars aren't just fascinating because of their density and magnetic fields, they're also incredibly violent. Occasionally, a magnetar will experience what's called a starquake, a sudden shift in its crust caused by the immense stresses of its magnetic field. These starquakes release bursts of energy so powerful that they can be detected across the universe, even from billions of light years away. In fact, some of the brightest flashes of gamma rays ever observed have come from magnetars, making them key players in the study of high-energy astrophysics. What's truly remarkable is that magnetars are relatively rare. Out of the billions of neutron stars in the universe, only a small fraction are magnetars. This rarity makes them even more intriguing to scientists who are eager to understand how they form and why they are so different from other neutron stars. Studying magnetars not only helps us learn about these extreme objects, but also gives us insights into the fundamental laws of physics under conditions that we can't replicate on Earth. As we continue to explore the universe's most extreme densities, magnetars stand out as a testament to the incredible forces at work in the cosmos. Their combination of density, magnetic power, and explosive behavior makes them one of the most fascinating objects in the universe. Next, we'll venture into the speculative realm of the multiverse, where varying densities across different universes could hold the key to understanding the very fabric of reality. Stay tuned as we unravel this cosmic mystery. Now, let's shift our gaze beyond the boundaries of our own universe and into the realm of the multiverse, a concept that stretches the limits of our imagination. The idea of a multiverse suggests that our universe might be just one of countless others, each with its own unique properties, including density. In some of these universes, the density could be so high that matter is packed into unimaginably small spaces, while in others, it might be so low that galaxies barely form. This variation in density could hold the key to understanding why our universe has the fundamental constants and laws of physics that it does. Imagine a cosmic tapestry where each thread represents a different universe, each woven with its own rules. In some threads, the density is so extreme that stars and planets form in ways we can't even begin to comprehend. In others, the density is so sparse that matter is spread thin, creating vast, empty expanses. These differences in density could explain why our universe has the precise conditions necessary for life to exist. If the density were even slightly different, the delicate balance of forces that allow atoms to form and stars to shine might never have come together. One of the most intriguing aspects of the multiverse theory is how it ties into the concept of fundamental constants, numbers like the speed of light or the strength of gravity that seem to be finely tuned for life. If there are countless universes, each with its own density and physical laws, it's possible that ours is simply one of the rare ones where everything aligned just right. This idea, known as the anthropic principle, suggests that we observe the universe the way it is because it's the only way we could exist to observe it. But how do scientists even begin to explore such a speculative idea? While we can't directly observe other universes, theories like string theory and quantum mechanics provide frameworks that allow us to imagine how a multiverse might work. These theories suggest that the density of each universe could be determined by the way higher dimensional spaces fold and interact, creating pockets of reality with wildly different properties. It's a mind-bending concept, but one that could help us understand why our universe is the way it is. As we ponder the density of the multiverse, we're reminded of just how much we still have to learn about the cosmos. The idea of countless universes, each with its own density and laws, challenges us to think beyond the familiar and embrace the unknown. Next, we'll dive into the mysterious Higgs field, a fundamental force that permeates the universe and gives particles their mass. Stay with us as we uncover the secrets of this invisible yet essential part of reality. Now, let's turn our attention to something that might sound like science fiction, but is very much a part of our reality: the Higgs field. This invisible field stretches across the entire universe, and without it, the world as we know it wouldn't exist. The Higgs field is responsible for giving particles their mass, which is why it's often referred to as the cosmic molasses that slows things down and allows matter to form. Without it, particles would zip around at the speed of light, never clumping together to form atoms, stars, or even us. But how does the Higgs field relate to density? Well, the field itself has a kind of energy density that fills the vacuum of space. This isn't the kind of vacuum you might think of empty and devoid of anything. Instead, the quantum vacuum is a seething, bubbling sea of energy and particles popping in and out of existence. The Higgs field is part of this quantum vacuum, and its energy density plays a crucial role in shaping the fundamental properties of the universe. It's like the invisible foundation that holds everything together, even in the emptiest regions of space. What's fascinating is that the Higgs field isn't uniform everywhere. In some theoretical models, variations in the field's density could lead to dramatic changes in the laws of physics. For example, if the Higgs field were slightly denser or less dense in certain regions, it could alter the mass of particles, potentially making atoms unstable or even preventing stars from forming. This delicate balance is what makes the Higgs field so essential to our understanding of the universe's structure and its extreme densities. Scientists discovered the Higgs boson, the particle associated with the Higgs field, in 2012, marking a monumental achievement in physics. This discovery confirmed the existence of the field and gave us a glimpse into how mass is generated. but there's still so much we don't know. For instance, why does the Higgs field have the specific density it does? Could there be regions of the universe where the field behaves differently? These questions push the boundaries of our knowledge and remind us just how much we have yet to uncover. As we explore the density of the Higgs field, we're reminded of how interconnected everything in the universe truly is. From the tiniest particles to the vastness of space, the Higgs field is a silent yet powerful force that shapes the very fabric of reality. Next, we'll venture into the turbulent world of quantum foam, where space-time itself becomes a chaotic, ever-changing landscape. Stay with us as we dive into this mind-bending concept that challenges everything we think we know about density and the nature of the universe. Now, let's take a step into the bizarre and unpredictable world of quantum foam. Imagine space-time not as a smooth, unbroken fabric, but as a turbulent, frothy sea, constantly churning at the tiniest scales imaginable. This is the essence of quantum foam, a concept that redefines our understanding of density and the very nature of reality itself. At these minuscule levels, space-time isn't calm or orderly. It's a chaotic, ever-shifting landscape where particles and energy pop in and out of existence in a frenzy of activity. This isn't just theoretical speculation. It's a consequence of the strange rules that govern quantum mechanics, where uncertainty reigns supreme. So, what does this mean for density? In the quantum foam, the density of space-time isn't uniform or stable. Instead, it fluctuates wildly, creating regions of intense energy and matter that appear and disappear in the blink of an eye. These fluctuations are so extreme that they challenge our traditional ideas of what density even means. In this microscopic realm, the very fabric of space-time is riddled with tiny bubbles of energy, each one a potential universe in its own right. It's as if the universe is constantly rewriting itself at the smallest scales, creating a dynamic, ever-changing tapestry of density. But here's where it gets even more mind-bending. The quantum foam isn't just a curiosity of physics. It has profound implications for our understanding of the universe. For instance, some scientists believe that these fluctuations could give rise to wormholes, tiny tunnels through space-time that could theoretically connect distant parts of the universe. Others suggest that the foam's chaotic nature might hold clues to the unification of quantum mechanics and gravity, two forces that have so far resisted being combined into a single theory. The density of the quantum foam, with its wild fluctuations, could be the key to unlocking some of the universe's deepest mysteries. What's truly fascinating is how this concept forces us to rethink our assumptions about the nature of reality. We often think of space as empty and time as steady, but the quantum foam shows us that even the vacuum of space is teeming with activity. It's a reminder that density isn't just about how much matter is packed into a space. It's also about the energy and fluctuations that define the very fabric of existence. As we continue to explore this turbulent realm, we're left with more questions than answers, but that's what makes it so exciting. The quantum foam challenges us to think beyond the limits of our current understanding and imagine a universe that's far stranger and more dynamic than we ever thought possible. Next, we'll shift our focus to the universe's accelerating expansion and how it's reshaping our understanding of cosmic density. Stay with us as we explore how this phenomenon is not only stretching the fabric of space but also altering the very balance of the cosmos. Now, let's turn our attention to one of the most profound mysteries of the cosmos, the accelerating expansion of the universe, and how it's reshaping our understanding of density. Picture the universe not as a static, unchanging entity, but as a dynamic, ever-growing expanse, stretching itself thinner with each passing moment. This expansion isn't just a slow, steady process, it's accelerating, driven by a mysterious force known as dark energy. And as the universe grows, its overall density is changing in ways that challenge our understanding of the cosmos. At its core, density is a measure of how much matter and energy are packed into a given space. But as the universe expands, that space itself is getting larger, spreading matter and energy farther apart. Imagine blowing up a balloon with dots drawn on its surface. As the balloon inflates, the dots move away from each other, becoming less concentrated. Similarly, as the universe expands, galaxies, stars, and even the cosmic microwave background radiation are being stretched apart, reducing the density of matter and energy over vast distances. But here's where it gets even more intriguing. While the density of matter is decreasing due to this expansion, the density of dark energy appears to remain constant or even increase. Dark energy, which makes up about 68% of the universe, is thought to be the driving force behind this acceleration. Unlike matter, which thins out as space expands, dark energy seems to permeate the cosmos uniformly, maintaining its density even as the universe grows. This creates a cosmic tug-of-war. While matter becomes more diffuse, dark energy's influence grows stronger, pushing the expansion faster and faster. What does this mean for the future of the universe? If dark energy continues to dominate, the expansion will keep accelerating, leading to a future where galaxies are so far apart that they become invisible to one another. Over billions of years, the universe could become a vast, cold, and lonely place, with matter spread so thinly that star formation ceases and galaxies fade into darkness. This scenario, often called the Big Freeze, paints a stark picture of a cosmos where density, once a defining feature of the universe, becomes almost negligible. But the story doesn't end there. The accelerating expansion also raises questions about the ultimate fate of the universe. Could dark energy's behavior change over time? Could it eventually reverse, leading to a big crunch where the universe collapses back in on itself? Or could it trigger a big rip, tearing apart galaxies, stars, and even atoms? These possibilities remind us that the universe's density isn't just a static measurement, it's a dynamic, evolving property that holds the key to understanding the cosmos's past, present, and future. As we ponder these questions, we're reminded of how much we still have to learn about the universe. The accelerating expansion challenges us to rethink our assumptions about density, energy, and the very fabric of reality. It's a reminder that the cosmos is far more complex and mysterious than we often imagine, and that every discovery brings us closer to unraveling its deepest secrets. Next, we'll explore the density of the observable universe, bringing together all the threads of our journey through the cosmos's most extreme densities. Stay with us as we uncover the final piece of this cosmic puzzle. Now, as we reach the final chapter of our cosmic journey, let's bring everything together by exploring the density of the observable universe. This is where all the threads of matter, energy, and the mysterious forces we've discussed converge, painting a complete picture of the cosmos as we know it. The observable universe, the portion of the cosmos we can see and study, is a vast expanse filled with galaxies, stars, planets, and the invisible components that shape its structure. But what exactly is its density, and what does it tell us about the nature of reality? To understand the density of the observable universe, we need to consider everything it contains: ordinary matter, and dark energy. Ordinary matter, the stuff that makes up stars, planets, and even us, accounts for only about 5% of the universe's total content. Dark matter, which we can't see but know exists due to its gravitational effects, makes up roughly 27%. And dark energy, the mysterious force driving the universe's accelerating expansion, dominates the remaining 68%. Together, these components create a delicate balance that defines the universe's overall density. But here's the fascinating part. Despite the vastness of the cosmos, the average density of the observable universe is surprisingly low. If we were to spread out all the matter and energy evenly across space, the density would be equivalent to just a few atoms per cubic meter. That's an incredibly sparse distribution, especially when you consider the immense scale of the universe. Yet this low density is crucial for the cosmos as we know it. If the universe were denser, gravity would have caused it to collapse back in on itself long ago. If it were less dense, matter would have spread out too quickly for galaxies and stars to form. The universe's density, as it is, strikes a perfect balance that allows for the complexity and beauty we see today. This balance also shapes our understanding of reality. The density of the observable universe influences everything from the formation of galaxies to the behavior of light as it travels across billions of light years. It determines how structures like galaxy clusters and cosmic filaments form, and it plays a key role in the universe's expansion. By studying this density, scientists can piece together the history of the cosmos from the Big Bang to the present day and even make predictions about its future. As we reflect on the density of the observable universe, we're reminded of how interconnected everything is. From the tiniest particles to the largest structures, the cosmos is a tapestry woven together by density, energy, and the forces that govern them. It's a reminder that the universe, for all its vastness and complexity, follows fundamental rules that we're only beginning to understand. And as we continue to explore, each discovery brings us closer to unraveling the deepest mysteries of existence. With this, we've reached the end of our journey through the universe's most extreme densities. From neutron stars to dark energy, we've explored the incredible phenomena that define the cosmos. But the story doesn't end here. There's always more to discover, more questions to ask, and more mysteries to solve. So, what do you think about the density of the observable universe? Share your thoughts in the comments below, and don't forget to like, subscribe, and hit the notification bell for more cosmic adventures. Until next time, keep looking up. The universe is waiting to reveal its secrets. As we wrap up this cosmic exploration, let's take a moment to reflect on the incredible journey we've taken through the universe's most extreme densities. From the mind-bending density of neutron stars, where a sugar cube-sized piece weighs as much as a mountain, to the mysterious depths of black holes, where gravity warps space and time itself, we've uncovered some of the cosmos' most astonishing secrets. We've marveled at the remnants of stars like white dwarfs, pondered the hypothetical existence of quark stars, and even ventured back to the early universe, where everything was packed into an unimaginably dense point before the Big Bang. We've explored how dark matter and dark energy shape the universe's density, creating the cosmic web that connects galaxies across vast distances. We've witnessed the extreme conditions in the sun's core, where nuclear fusion powers our solar system, and discovered ultra-dense exoplanets that challenge our understanding of planetary formation. From the chaotic collisions of neutron stars to the eerie emptiness of cosmic voids, each fact has revealed a new layer of the universe's complexity. These extreme densities aren't just fascinating curiosities, they're the building blocks of the cosmos. They dictate how galaxies form, how stars burn, and how the universe evolves over billions of years. They remind us that even in the vastness of space, the smallest details can have the most profound impacts, but the story of the universe is far from over. Every discovery raises new questions, and every answer brings us closer to understanding the true nature of reality. So, what do you think about these cosmic extremes? Which fact left you the most amazed? Share your thoughts in the comments below. I'd love to hear your perspective. And if you enjoyed this journey through the universe's most extreme densities, don't forget to like, subscribe, and hit the notification bell so you never miss out on our next cosmic adventure. The universe is full of wonders waiting to be uncovered, and together we'll keep exploring its deepest mysteries. Until next time, keep looking up. The cosmos has so much more to reveal.